Yes, we will join very soon. I will also send a reminder on WhatsApp group, so they will be joining very soon. Meanwhile, you can start.
Definitely, definitely. Okay. Okay. Right. Right. I will start sharing the screen. Right. I guess you can see.
Yes, sir. We can see your screen.
Yes. Yes. Okay. Right. Let me take my tab a little bit high. Yeah. Okay. So in the yesterday's session, so we discussed about basically why do we need uh, to study the statistical physics, right? Okay. So as a quantum computing enthusiast, we need to understand how the quantum hardware is being designed, and hardware actually involves qubits. They are like physical quantities. Okay, they are so sensitive to the environment, and also they're sensitive to each other. I'm sorry. The way they interact with each other is actually dictated by uh, uh, just a minute. Yeah, actually dictated by the statistical physics, the laws of statistical physics. Remember, statistical physics in the sense I'm talking in terms of zoom out scenario, where if I just take a system consisting of many small entities, okay, I can develop the theory at a small entity and combine them and come up with a larger concept or larger view where small entities are captured together and create a macroscopic entity. Okay, so that is the statistical physics addresses. Okay, so within a statistical physics there is a minute layer, the division between quantum to classical to quantum. So that also we will touch for today. So the essence is, with the first half, is why do we need to study the quantum statistical physics for quantum computing research or understanding. So one important thing which just we got is the partition functions. There is a concept called partition function, which actually comes from statistical physics. That is very important. It leads to everything. Actually, it is like, say, the number one player or the center of attraction for everything. That has got everything. That would help us to study everything of quantum computing using statistical physics. Okay, right? So that is the motivation for statistical physics. Fine, let me close this. Is no more required for me. Okay, so then we went on to, just a minute. Yeah, we went on to start with the so do I need to enlarge? I think I will enlarge slightly bit. Yeah. Okay. So we went on to define what is a state, by the way. Okay. A state is collection of things, collection of particles, for example. Okay. And those things may interact with each other or they may not interact. Or you can say when they interact, I'm sorry, you can say they interact strongly or they may interact weakly. Okay, so when I say they interact strongly, probably that may happen in the solids, all right, or in the liquids. If I say weakly, means probably a gaseous material where the particles are located at different places. Okay, right? So if I have to define this system, I would, let's say, I would use a classical laws of physics where I can, classical laws of physics says I can see things with my naked eye and touch things and perceive it. So those kind of things, real world things, what we see around, we define using something called Newtonian mechanics or Newtonian laws or classical physics rules. Okay. At the most, I would be needing, for example, if I just take one entity, I would start specifying that entity with the position and the moment. Okay, right? So at the most, what I need two variables. Okay, I can develop other variables from this variable itself. If I want to have a kinetic energy, I can develop from the momentum. Okay, p square by 2m is the momentum for a kinetic energy. In that way, I can develop all other factors. Angular momentum I can generate. Okay, so how classical mechanics is going to be complete when it comes to describing a system is, if I know the variables, classical variables, let's say position, momentum at given time, I can predict and I can find later on using Newtonian laws itself. Okay, basic equations of motion I can use, I can find that. Now, quantum mechanically, if I want to do that, let's say I want to get into the much details and smaller quantum level, what I have to do, let's say I want to talk in terms of atomic level, things are not certain anymore. Just like a classical way, there is everything is certain. Here it is not certain because of the something called a duality gets into the system, where the tiny particles like electrons behave like a waves as well as matter. So the waves associated with these particles is actually derived or represented by de Broglie wavelength, lambda d, like I showed you here. And one more, why this duality comes here, because so things are so tiny, you can't exactly locate their position and find their velocity exact. There is always chance of making a mistake. That is actually the product of errors in the position, product of errors in the momentum together is going to be always larger than some quantity, which is a Planck's constant h cut. Okay, h cut is h by 2 pi. Okay, fine. Okay, so in some places they say h by 4 pi, and so just a small scalar change. Now, in this particular case, I can't just simply rely on this position and momentum. I have to define the description of the wave nature by using a mathematical function called a wave function, which is now going to be depending on the position operators, or now I am calling operators, because in quantum physics, the position becomes a position operator, momentum becomes momentum operator, energy becomes energy operator. Okay, we will put a hat on that. So the wave function used to describe a quantum system would be a function of all the coordinate variables, operators. Okay, so here these operators could also consisting of the spins, angular spins or the rotational spins. All those things can come into the picture. Okay, how this is going to be complete is, if I know a given wave function at a given time, I can always find in later time using the Schrodinger equation. Okay, so the Schrodinger equation in general I have given here, right, where I have a spatial derivative. That means even I can predict in space how the wave function is varying. And also on the right hand side, I have a temporal derivative, which helps me to find the temporal dynamics of the wave function. Okay, and if you see carefully, this wave equation, sorry, this Schrodinger equation could be solved if I separate them into spatial and temporal individually. That is possible. Okay, for a given system. In that case, if I represent the total energy of the system in terms of kinetic energy and potential energy in the operator form, it becomes an operator called a Hamiltonian operator. In that case, so the operator form of this spatial derivatives and u would be captured into the h operator, and only will keep the time derivative as it is. And what I can do, I can solve that equation, one-dimensional temporal equation, and find the solutions for the wave function. Here you see the wave function in time. If I know initial wave function, I can derive in the future wave function. which is simply is actually multiplied by a transformation operator. It's called a U operator. You already come across this. It's a unitary operator, which is U is equal to minus I into exponential minus I into H into TF minus TI divided by H cut. Okay, so this derivation probably you might have come across already. So I'm just borrowing or just revising needed for our statistical physics understanding. Okay, so the quantum physics becomes complete with the Schrodinger equation. Okay, now let's take a few like one simple example, like let's say electron revolving around the nucleus. Okay, right? It can revolve forever, and it constitutes a magnetic field because of the rotational dynamics, and also it can rotate about itself. Because of that, it again constitutes a spin magnetic moment. If it is rotating, let's say in a clockwise, I can associate the direction perpendicular to the clockwise as a positive, and the opposite to the circle, right, equatorial circle, I'll associate negative. Okay, so here in this case, in the spin, in the case of particularly electrons, the spin would be plus half and the minus half. Okay, okay, just a minute, there is a chart message, let me see. Sir, how the time evolution is described in Hamiltonian is slowly changing with time. No, I never said it's not slowly changing with time. Okay, it can change rapidly also, right? Okay, how the time evolution, okay, is described slowly changing in time. Okay, I'm not getting exact question what you mean, but here you see this is this exponential minus I h into TF minus TI divided by h is the time evolution operator. If I multiply that operator onto the old quantum wave function, I would get the new one. Okay, so how do I get this? Actually, it's a simple integration. If you do it, you will get that. Okay, so I think I'll quickly show how it is done. Okay, so fine. So like, okay, so let me take a separate part. Okay, so the question is how time evolution is done, right? Okay, so let me say there is a quantum system. Let's say for time being, I only worry about the time dependency. Okay, right? So the quantum system is described by Hamiltonian operator, which is usually a kinetic energy plus potential energy in operator form. Okay, right? So which is described by H operator form. Now, what exactly the operator form would help me to do is, it is in a matrix form, its operator is matrix. If H acting on some quantum state is equal to energy with which it could exist multiplied by the quantum state itself. It is a simple eigenvalue equation. Eigenvalue equation. Okay, it's also called characteristic equation. Now, in quantum physics, what happens? The E actually takes an operator form, which is actually plus IH cross dou by dou t, time derivative. So in that case, what happens? H rho psi is equal to IH cross dou by dou t into psi. Right? So now if you see, if I have a first order differential equation, okay, so I'll just interchange the things or rearrange the things. What I will do, derivative of the partial derivative of psi divided by psi is equal to, right, IH cut, okay, Hamiltonian multiplied by dt. Now I can integrate from some time t initial to t final. So t initial to t final. Okay. So on the left hand side, I'll get a log of psi, which runs from t initial to t final. On the right hand side, I have IH h into t. Let's assume that h is independent of time. Okay. In that case, I can bring it out and just integrate the time. So which runs from t initial to t final. Okay. So on the left hand side, I'll get log psi at t final minus log psi at t initial equal to IH Hamiltonian TF minus T initial. Okay. Now log A minus log B I can convert into log TF T initial. Okay. Right. Is equal to, right, minus IH cross, same thing, TF minus T initial. Okay. I can send the log to the right. Okay. What happens? Wait a minute. Did I miss plus sign here? Plus. Okay. If I send the log to the right, what happens? Psi of t final divided by psi of t initial is equal to exponential IH Hamiltonian TF minus t initial. Okay, right? So yeah, right? And t final is equal to psi of multiplied by EIH cross. Okay, right? So this is what I mean. Okay, so basically some minus sign or plus sign is somewhere is missing, but don't worry. Okay, so this is what the unitary operator is. If I multiply unitary operator, if it is not in the Ket notation, means the psi of t is some functional form. So I can just multiply u on the any side because u is just another expression with the h being taken, h taking the expression like this form. Okay, right? So whatever is there in the bracket. Okay, if it is in the operator form, which is in the matrix form, where I'll have a Ket notation. So what is exactly Ket notation is t final is equal to unitary operator psi of t initial. This is what I'll have. Okay, right? If it is in a expression form, right, this will have. Okay, fine. Let's come back. Fine. So this is what I wrote. There is a minus sign somewhere I missed. Please cross check that. Now, if you see, I hope that I answered that question. It's not slowly varying. Okay, it's a time evolution in terms of Hamiltonian. Okay. Now, if I just take an electron which spins around, it can have positive spin or a negative spin, up spin or a down spin. So that could be captured in the wave function psi itself as a one of the degrees of freedom. Okay. So let's say if I have one atom or one electron along with Q1, Q2, Q3 and P1, P2, I will add a MS1, MS2 and MS3, right, corresponding to all the atom. If I just take one mole of electrons or atoms, let's say hydrogen atom, one electron is contributed, there what is the wave function corresponding to all the electrons contributed from a collection of hydrogen atoms would be psi, depending on all the locations of the electrons and their corresponding spin moments, right? The spin contributions, like I look MS1, MS2 and MS3 and so on up to this whatever number I'm talking about. Okay, right? So now another one. If I just see, so far here I'm talking about single atom, collection of atoms. Let's say if I just take like atom in the higher periodic table. So let's say there, apart from the excited state, it can also access, the electron can access the other excited states. So using quantum physics, you can derive what are the possible energy states for that. So that is being given here as En, which is equal to n plus half into h cut omega, where n would stands for the ground state energy, excited and so on. Okay, so here n is actually called principal quantum number, and where ms earlier it's called a spin quantum number. Okay, So I can also have angular momentum quantum number, okay, L, which is also comes in the, okay. So these things together would describe quantum mechanical nature of a single quantum particle. Okay, so why did I bring quantum physics is I'll start studying single things quantum mechanically and combine them. I'll derive a macroscopic, a large thing. Okay, fine. Now, so let's say quantum particle is confined into a three-dimensional space, a box. In that case, the Schrodinger equation takes into this form. Okay, right? Whatever is shown here in the bracket, right? Okay. So, and this is just a second order linear differential equation, remember. So these equations would have sinusoidal solutions, and see the wave function should vanish at the boundaries. So that condition I would use to define or describe or obtain what are the amplitudes or the constants involved here. Okay, so though using those constants I can get what is the energy states the electron could exist if it is placed within a three-dimensional box. Okay, so this is slightly different. You see how different this is. This energy from electron can exist within a single atom. Okay, right? So just please mind the difference. Now, now what is the quantum mechanically things are different. Classically from the zoom out case is different. Okay, so when I put an electron within a three-dimensional box means I am not saying single electron, I'm putting so many electrons. So the energy here, the expression which I have shown here, probably comes from contributions from all the other atoms. Okay, so that would become a classical version of energy. But when I talk about a single atom within an atom, with single electron within an atom, I'm still only talks about a single electron within an atom. So where the energy is quantum mechanically expressed or explained using something called harmonic oscillator, quantum harmonic oscillator. Okay, we'll slightly touch that in today's class. Okay, fine. Now, fine. So how I am shifting between classical to quantum, is there any analogousness between quantum to classical? Of course, there is a very simple way I can connect them both. So one way of connecting is using de Broglie wavelength, like I said. If I start from, let's say, tennis ball, the wavelength associated, quantum wavelength associated with it, or quantum wave associated with the tennis ball is very, very tiny. Let's say 10 to the power of minus 25 meters. So tiny you can't measure the wavelength. If I go a little bit smaller, let's say moving bullet, it's like 10 to the power of minus 22 or 23. That is again very small. It's still non-measurable compared to the ball, cricket ball. It is reasonably fine. If I go to the electron, which is traveling with the velocity of the light, and its mass is 10 to the power of minus 35 kilogram, there the wavelengths are the frequencies, and the wavelengths would be associated with optical frequencies, the waves. So I can easily measure them, which are then the angstrom wavelength. Okay, so that is why, because electrons would possess a wave nature, but not the bullet, not the cricket ball. Remember that. Okay, so even if I use high speed high motion cameras, you can see about the bullet, you see some kind of a, like say, some kind of a circles around. It's like a disturbance is traveling. Just like when I go to a pond or lake, I just drop a stone, you're going to create a disturbance, a waves. Similarly, the electron is going to, like a moving bullet could create a slight a wavelength which cannot be seen for the naked eye. Okay, fine. Now the distinction between, sorry, the connection between quantum to classical, or you can say classical to quantum analog. Okay, for example, if I just take a single particle classically, how do I define it? I'll define by its position and momentum. So if it moves in this momentum, in this space, position and momentum space, just like three-dimensional, two-dimensional surface, things move, right? Okay, so right, things move. So here, instead of two-dimensional x and y plane, I call it as a coordinate position plane, position direction, and the momentum direction. So here, if I divide the entire surface, position and momentum surface, into small chunks, small elements, take a delta q into delta q into delta p. Let me call a small element h naught. If I do that, okay, So it is actually the particle is hopping between one element to other element. So if I know the initial element location, I can find a later element by just adding all the small elements to the old values. In this way, you can predict the future. Okay, that is the classical way of doing it. Okay, so remember how small you can take, right? The element, the small cell element H0 would give you better accuracy for you. But when it comes to quantum mechanics, you can't exactly specify position and momentum. So there is always delta Q, delta P, always greater than h hat. So your small element you were to take in a classical scenario cannot be smaller than the h cross, which is always more than that. So that is the connection or the analogy between classical to quantum case. So when you want to move from quantum to classical, you should mind how small things can be, how accurate things can be specified. Okay, fine. So now statistical ensemble, let's say a collection of things. How do I treat? I use again a wave function quantum mechanically, or I can use a collection of coordinates classically. Okay, right? Now, not only that, the system also described by things like energy, pressure, a magnetic moment. Just now I just showed you. Okay. So these are like macroscopic parameters used to describe the system. Okay. For example, if I just take a paramagnetic material, or like a paramagnetic by nature, it's a paramagnetic, not fully magnetic. Okay, or not contributes 100%, because the atoms, individual atoms, their outermost electrons would contribute certain magnetic moment by aligning into particular direction. Not all will align in the same direction, some would align opposite, and like that. Because of that, there is a total magnetic moment always less than fully aligned situation. Okay, so here at a given point, if I just take a paramagnetic material, collection of atoms or the electrons, the spin electrons, you say, right? So there is always alignment complete, alignment partial, alignment less partial, and so on. So the magnetic moment always range between certain value, certain full mu m to mu m plus delta mu m. Okay, so right, so I would say there is always certain number of accessible states exist for the entire system. Let's say if I just take 10 out of 10, 8 may align and 2 may misalign, 7 may align, 3 may misalign. So in this case, there are n factorial ways I have aligned them, means there are n factorial number, 10 factorial number of accessible states available for this paramagnetic material to exist in. Okay, and moreover, if I confine that from the environment, okay, and if I confine that from the environment, what happens? It becomes equally like all accessible states are becomes equally likely, means all are equally probable. Okay, if you ensure there is nothing interacting with it. Okay, and also here there is a catch. You have to assume that there is no internal interaction. As if the atoms, like electrons, would feel there is nothing around. Okay, so that is an approximation, by the way, means they are so far it's like ideal gas. Okay, so the statistical physics itself, in the mechanics, there is a postulate: isolated system in equilibrium will have equally likely states, right, in its accessible form. So all are equally likely. Okay, right? So one example I just gave you yesterday, right? So let me summarize that example here. If I just take 3 spin particles, right? So all are equally likely, and the total energy, you see, the total energy would range from minus 3 mu h to plus 3 mu h. Okay, so the window is so large here. Okay, and let's say I induce, right? I induce some external magnetic field. In that way, I'm forcing the system, let's say, to have an energy minus mu h, total energy. In that case, what happens? Okay, only 3 states, accessible states, would come into the picture. Okay, so alignment would again, one of them misaligned, and which one I don't know, which can vary between all the 3, right? So there are 3 states available, accessible states here. And what is the chance of, if there is no magnetic field, everything is equally likely, like I was showing here. Okay, if there is a magnetic field, right, if there is a magnetic field, right, so only few of them are favored. In this particular case, 2, 3, 4 are favored with an energy minus mu h. Fine. Okay, so what the thermodynamics law says about these things, if you see, if two systems, if I just take two systems together, such systems together, and the third system also there, let's say third system is in contact with the A and B, first two systems, third system happen to in the equilibrium. Okay, in that case, the first two has to become equilibrium with each other. That is the zeroth law of thermodynamics. Okay, so on the second, there is a first law of thermodynamics which says, if there is a microsystem which is in equilibrium characterized by some mean energy E, or the internal energy E, if it is isolated, this energy is always going to be constant because there is no one to give the energy. So only thing is the internal energy has to retain the same. Okay, right? And if it is an external interaction is there, some external heat is given, the probability system would do some work by rearranging, so that rearrangement would consume some energy. So that's why there will be a change in the internal energy. How much it is delta E is equal to minus omega plus Q, right? Some energy is added, some energy is removed for the rearrangement, so that much internal energy changes would happen. Okay, right? That is the first law of thermodynamics. The third law of thermodynamics says, sorry, second law of thermodynamics says, if the system is in an equilibrium, okay, which is always characterized by an entropy, the orderness in the system, so this orderness would always keeps increasing, right, when the system is isolated. Okay, when the system is not isolated, so there is a change in the disorderness would be connected to how much energy is acquired from the external means. That is a change in entropy. The disorderness is ds is equal to dq by dt. Remember, having said thermally isolated, the entropy would increase. If you decrease the temperature to smaller levels, the entropy would go and stabilize and saturate and become constant. Okay, so that also we'll see, right? So now the third law of thermodynamics says, again talking to the entropy, right, if your temperature goes to smaller and smaller value, the S would become a constant. Okay, so in the microscopic systems, the property is, okay, the S is actually represented in terms of K into log of the number of accessible systems, accessible states available for the system. We'll just understand more into the number of accessible system omega in today's class. Okay, right? Fine. So let me start. This is a revision what I just did yesterday's revision, and let me start. Okay, right? Okay, access. I want to know about accessible systems, right? Okay, I just gave a title canonical ensemble. Let's just forget about for time being what is this. Okay, so let's say first of all try to understand things one by one. Let's say I just want to understand ensemble. Ensemble means what? Collection of things. Okay, which could be electrons or atoms or even photons or atoms together would create what? A solid. It's a macroscopic object. This is a microscopic. This is a microscopic. Okay, fine. Now, collection of such things I'm talking is an ensemble. Why the name canonical? Let's say if the system which I have taken, let's say system I have taken, it consisting of small things. Okay, if the system has, right, some number n number of entities inside, Okay, right? Audio is clear now. Okay, yeah, right. So if the system has n number of particles and it is confined within a volume V, and its temperature, let's say, set to T, it is not interacting with any surrounding environment, so it is standardized. The system is standardized to exist in the same form without changing its energy, unless the rearrangement could lead to different energies, but overall energy could remain for a particular arrangement. The fixed energy would be there. Okay, so the collection of these things standardized form is actually called canonical ensemble. Okay, because it is in the equilibrium. Remember, equilibrium, which ensures these things to be fixed. Okay, fixed means n is not going to change, no additional atoms will come, volume is not going to change, because if your volume is changing means they're spreading around. I'm not creating that king. Temperature I'm not increasing. Okay, so the fixed, so the such collection is called canonical ensemble at a equilibrium. Okay, now again, the rearrangement would lead to some change in the energies. Okay, let's say all arranged properly or in form would have energy E, and then just misalignment or something would add or subtract some delta E part. Oh, is this? Yeah, right. So the energy is always fluctuate between, sorry, a given energy always fluctuate between E to E plus delta E. What I mean by R is one arrangement I'll represent by R1. For that, there is a ER equal to 1. For R2, there is one more E. Okay. For R2, I'll have, sorry. For R2, I'll have, yeah. What happened? Okay, let me restart the pen. Yeah. I'm sorry, guys. So when I touch my hand to the bottom, it is actually acting weirdly. Okay, let me start a new page probably. Okay, let me start a new page. Okay. Yes. Okay, where I am at. Okay, so the energy fluctuates between, okay. Sorry, I'm sorry. Yeah. Okay, and this is something weirdly acting. Okay, let me reload. Oh. Yeah. So ER fluctuate between E to delta E. Okay, right? So the how many such ERs would exist, which let me call it some number, okay, some omega. So E of omega of ER means the number of states accessible for the system to exist in particular set of arrangements. Okay, very, very important. Now, if the system is isolated in the case, all of them are equally probable. Okay, so the probability would be PR is, let me call some constant probability. Okay, some C into 1 constant. That is, if E is between E plus delta E. Okay, otherwise the probability is 0. Otherwise, so this is for the isolated scenario, isolated situation. Okay, now let's talk about when it is interacting with environment. Always think in the terms of a qubit within a transpose circuit. Okay, a trapped ion within like the electromagnetic field traps or laser traps. Okay, so I'm talking in that context. I'm trying to address that. Now let's say, now let me give a name to the system. Let me call system is A, gets into the interaction with the reservoir A prime. Okay, let me call it reservoir. Atom in a lattice. Lattice is a reservoir, atom is the system. Now let me say overall system would be, okay, overall system, okay, I have to maintain some difference. Overall system would be, let's say, this is, let's say, A and A double prime. A prime plus A double prime. Overall system. Okay. Now, this overall system, what happens? Because of the interaction, some energy would come to the system, and system from the heat reservoir. Okay, but reservoir may not change much. So what I will do at a given instant of time, let's say this is the system. Okay, and as time progresses, system would just say evolve. Let's say A1, A2, and A3, and so on. Evolution, evolve. Okay, right? Now, how many states are accessible for a system? Okay, that's the question. So we just saw the number of states accessible is from the, okay, from here, the number of states accessible from here. Okay, right? Now, because of the environment also in the picture, what happens? Let's say E is the overall energy of the system at a given point, right? Okay, so this overall energy would range between this value to some delta E change. What is this delta E change? Because of a rearrangement. Okay, right? So now this is a overall system plus reservoir case. Okay, now since the things are conserved, energy is conserved, energy cannot go anywhere, reservoir to system and system to reservoir, but overall system plus reservoir overall energy should remain the same. Okay, so let me write down that E of 0 is equal to the system energy plus, let me call, reservoir energy. Okay, right? Now I can get the reservoir energy as overall energy minus system energy. I might not use double prime in the notes. Please don't confuse. If you read through, you'll understand. Just for understanding here, I'm just giving you that. Okay. Now, how many such these things E double primes are available? Because this E double primes also varies, right? How many such things are available for the entire system, which is simply equal to how many number of see, the system would exist with certain number of ERs, omega of ERs. But now the question is, overall system, how many states available for that? Okay, I would simply say omega of omega prime, sorry, double prime, E of 0 minus E of R. Very simple. Okay, so which is corresponding to the energies E double prime, E of 0 minus E of R. Okay, for corresponding to every of this energy, there is one associated set. So these values would vary within some range, so that many number of associated sets are available. Okay, now what is the probability of existing in a particular state would be PR directly proportional to this number of states, right? Okay, fine. Now let me put in some constant of proportionality. Let me call C double prime omega prime, sorry, double prime E of 0 minus E of R. Okay, so usually the C is found, double prime found by imposing the conservation of probability, total probability, right? Okay, but here if you see carefully, E of R is always much smaller than overall system, because overall system is consisting of what? Reservoir. Okay, so always is so small, right? Now, and one more thing you can say, E of is roughly equal to E double prime, right? So that means if I just take this function, the number of states available, E of 0 minus ER, you just see, right? It is a function I can expand in terms of about, let's say, some E of 0, right? I can expand. So this function is the system is so large, the reservoir is so large, this number of available states also very large, degrees of freedom of reservoir is so large. So what I'll do to reduce to slowly varying or a smaller function, I'll just take a log just for convenience. Okay, and there here have a log of some sigma omega double prime. So I can expand this omega double prime around E of prime, right? So E of double prime expand, right? Expand about E double prime is equal to E of 0. I can do that. So which is E equal to Taylor's expansion, the term as it is at what value? Omega double prime E of 0, right? Which is basically, I substituted E double prime equal to E of 0 minus the derivative of with the E double prime log omega calculated at what point? E double prime is equal to E of 0 multiplied by small quantity, whatever is I am having. Okay, so that is E of R plus other terms. Remember, other terms, let's say like another term. So the next term would be E of whole square will be there divided by 2 factorial. Remember, E of R is very small, very small. Okay, which means Very small means this term, the higher order terms implies higher order terms goes to 0. Okay, which implies that means what I have, log of omega double prime E of 0 minus ER is equal to log of omega double prime E of, okay, E of 0 minus, okay, what I'll have is just a derivative of log omega double prime E of, okay, into ER. Okay, if you carefully look at this term, second term, right? So derivative, okay, remember I have to put E of double prime is at E of 0. Okay, so derivative of log omega double prime E of, if you just take this term, okay, right, carefully if you see, which is appears to be like a 1 by Boltzmann constant into temperature. Okay, so which is actually beta, right? So dimensionality wise it appears to be 1 over thermal energy. This is thermal energy. Okay, right? So that means I can say right hand side is equal to, right, log omega double prime E of 0, right, okay, minus, okay, log sorry, what I have, derivative of, okay, let me put that explicitly what I mean. So 1 by k beta, 1 by k beta, so 1 by Boltzmann constant T, so which I'll put it as into ER is there, na? So what I'll have is log omega double prime. Let me exclude whatever is there inside for my comfortability, minus beta into ER. Okay, this is what I have. Now on the left hand side I have a log, okay, what I have is log omega double prime E of 0 minus ER. Okay, so let me take exponential on the both the sides, the send the log to the right, the left log to the right. What happens? E of 0 minus ER is equal to omega double prime, which is at the E of 0, exponential minus beta ER, right? But by the way, what is a PR? PR is, okay, C prime, right? Omega double prime, this quantity. Okay, now what I'll do, I can just take these two, right? It's a constant, right? I can just say some C exponential minus beta ER. I can just capture into the some constant, and now I'll find that exact constant using summation over R PR is equal to 1. So interestingly, what C comes out to be is, C is summation over R e to the power of minus beta ER. So the probability is e to the power of minus beta ER divided by exponential summation over EBR. This is the probability of any given system, right, which is a combination of reservoir and a heat, could exist with a particular state. Okay, how it is done is, I'll count all the states with a particular energy, ER, divided by all the existing energies, all the possible energies. So it's like probability. If I just take, there is a, let's say I have a let's say I have, what is the probability of getting a red color from the WebGR? Let's say 1 by 7. Okay. So let's say I have a 10 colored balls, out of which there is 2 red color, 2 blue color, okay, 2 brown color, 2 green color if I have, and everything else one individual. So there is a probability of coming red is 2 by 10. What? Okay. So likewise, I'm just counting the number of accessible states with ER divided by all the accessible states. Okay, ER can range in from some E to E plus delta ER. Okay, right? So here, if you just carefully see whatever is there in the denominator, right? Let me call that some Z. Okay, which is actually counting all the possible energy, all the accessible states with all the possible energies. So this is called partition function. It captures everything about the system, not particular energy value. It collects all the R's. See, you see, all the arrangements are captured. So it's a partition function, just similar to the density matrix which we had in the quantum computing, the outer product of a quantum state. Huh? The way density matrix does everything for us in quantum computing, in the statistical physics, the partition function does that. It helps us to calculate anything. Okay, right? Any physical parameter could be calculated with it. Remember, it is just counting the number of accessible states with various energies, where energy ER could range. Okay, so that is important, right? Fine. Now this is called, this distribution, this probability distribution called canonical distribution, because it is describing canonical ensemble, right? And also it is called a Gibbs distribution. Okay, or Gibbs principle. This is called Gibbs, the formula called Gibbs principle. Okay. Now, if we just try to understand what is this P is actually consisting of. Okay, right? For example, let me fix ER is equal to some E. Right? In that case, like what I'll have PR is equal to exponential minus beta into E divided by, okay, right, a summation of R into beta ER. So all, let's say, E's. Okay. So if you just carefully see this, the probability of existence of system with the energy E is simply equal to the number of accessible states with the energy multiplied by PR. Okay, right? So here, what is PR? PR is exponential minus beta E. Okay, the summation of all these, let's say it will take one value. For the time being, this is the one which is very important for us. If you just see, sigma E is increasing function. Sorry, omega of E is increasing function, rapidly increasing function, right? It is just like rapidly increasing, because as the system size grows and goes, many possible states will come, accessible states would increase, right? So increasing function. But if you just say minus beta E is actually a decreasing function, exponentially decreasing function, you see, because of the negative side. So when you take a product together, what happens? I would have, for some time it increases, sometime decreases. At some point it just peaks. Okay, at what point it peaks? Let me call some mean energy, or you can represent quantum mechanically with the left angle, right angle. Okay, right? So now if E is large means, okay, it peaked to very thin, like say delta function, very thin. Okay, implies thin delta kind of a function. Okay, if E is small, then I'll not have that kind of a sharp peak. Okay, now let's try to understand for paramagnetic case, which we have done, we have considered earlier. Let's say if we just take an electron, if it upspin, its magnetic moment is mu per positive upspin, okay, minus mu for a minus downspin. Okay, upspin represented by plus, downspin represented by minus. Right? Now, what is the energy associated if it is put in a magnetic field? What is the energy associated? Well, if it aligns along the magnetic field, is minus of the magnetic moment into applied magnetic field. What is the energy of the energy of the electron, which is aligned opposite, is minus of its magnetic moment multiplied by, so which is actually mu of h. This is minus mu of h. Okay, now the question is, what is the probability of electron could exist with upspin? Is exponential minus E plus. Very simple. You remember, you just like keep into your head, always exponential minus beta into the energy would tell me the probability. Okay, and if I multiply it by C, there's a probability density, that is a C is actually 1 over Z, the partition function, that would become, that would give me a density, probability density. Okay, right? In this particular case, C multiplied by exponential minus beta mu h. P minus would be C into beta E minus equal to C into E plus, okay, this yeah, wait a minute. Oh yeah, minus of minus, I'll get a plus here, minus of minus, I'll get a minus here. Okay, right? So there is a minus here and there is a plus here. Okay, so that is what I'm writing here. Fine. So beta mu h. Now, if I want to find mean magnetic moment, okay, so mean magnetic moment I want to find, which is probability of existing in the upspin, corresponding magnetic moment, plus probability of existing in the minus spin or a downspin and corresponding magnetic moment, divided by total sum probabilities, which is mu into exponential beta mu h minus mu h. I take a mu common, I'll have this. In the denominator, I have plus exponential minus beta mu h. Okay, which is simply mu is equal to mu into tan hyperbolic mu beta mu h. Okay, if you carefully see, beta mu h is actually mu h divided by k beta t, which is the ratio of magnetic energy and thermal energy. Okay, right? Dimensionally it is, no dimension is there, but if magnetic energy is larger than thermal energy, means mu h divided by k beta t, let's say, is like this. Sorry, opposite. The temperature is so high, magnetic momentum is small. Okay, high T, high temperature. In that case, what happens, right? Exponential of mu h by k beta would be 1 plus y and so on, right? Okay. And what I can simply get is, sorry, 1 minus, yeah, 1 minus. So tan hyperbolic y, let me call this is a y, okay, is equal to 1 plus y minus 1 minus y divided by 1 plus y. I'm just trying to put these things, okay, plus 1 plus y. So what I'll get is 2y divided by 2y, 2 gets cancelled, I'll get y. So magnetic moment mean value is mu into y. Y is what? Mu into h divided by k beta into t. Okay. So you see, by knowing the probability distribution, I can find out what is the mean magnetic moment, and I can also find mean magnetization and mean energy in the system. If you carefully see magnetic moment, if I want to find which would be increasing and just saturizing magnetic moment, mean magnetic moment for a given h by t. Okay, let me put express mu h by k beta. Fine. Now, like I said, I can also calculate the mean energy. Okay. Let's say I have PR, which is exponential minus beta ER divided by summation over minus beta ER. This is a Gibbs distribution or canonical distribution I have. Now I want to find what is the average energy, or I usually write E bar also. Okay, how do I want to find is, I just simply, what I'll do is sum over R ER minus beta ER divided by exponential minus beta ER. Very simple. Like what we did for the just a single spin case. See this one, magnetic moment, mean magnetic moment, and mean magnetic energy. Mean magnetic or internal energy, you can say. Okay. Now I can play a small trick here. What is the trick here? Let's consider the numerator. Okay. Numerator is ER exponential minus beta ER. Okay. Which I can write as, okay, minus summation d by d beta exponential minus beta ER. I can write that. Okay, it's fine, because derivative of exponential I'll get with a beta derivative, right? I'll get a ER. Okay, I'll get a minus sign, so I'll capture the minus sign by putting a minus sign. Okay, by the way, I know this is a quantity called a partition function. Okay, so let me write E bar is equal to minus, okay, okay, let me remove this part. Okay, is equal to what I have, 1 by z, this quantity, multiplied by summation over d by d beta ER. Okay, so which is minus 1 over z, okay, dz by d beta. Very simple, you see. Okay, I can even further go and simplify the things. Which way? 1 by d beta log of z. So log derivative with this would give me this. If I substitute z is equal to exponential minus beta, sorry, summation over exponential beta r. If I derivate that, okay, so I'll get this fact. Okay, so what it's saying is energy mean is just simply the derivative with the beta and the partition function derivative, not just the partition function, log of partition function. Okay, so now that is established. If I know what is the z exactly, okay, finding E is very easy. Just as simply minus dou by dou t. So dou by dou b log of partition function. Very simple. Not only that, you can also find the dispersion in the energy. Dispersion in the sense, if the energy, let's say the average energy is here, okay, how it is spread around, right? What is the delta E? That also you can find. How? You can just write delta E is equal to E minus average. Okay, right? And you can find the average of dispersion as, okay, which interestingly you are going to find is dou log z. You see, the power of partition function, it is going to give every physical quantity in terms of that. Okay, right? So I can also give one more thing. For example, okay, let's say I'm varying the energy of the system, right? Energy of the system. Okay, z is what? It is of summation over E minus beta ER. That means z is a function of beta and ER. It's a function of beta and ER. Okay, by the way, what is ER? ER is a function of position. Okay, ER is a function of position. I can conclude Z is a function of beta and X. Okay, depends on beta, that is temperature, and the position. Let's say log Z is there. Let's say if it is varying because of the change in the energy, right? Change in the temperature. So the log Z would vary derivative of log Z partially with respect to x into dx plus derivative of log Z with respect to d beta. Okay, right? So now you have two things here. I have two things here. Okay, so interestingly, let's say a system is encountering with a reservoir, so the internal energy is changing. Okay, so der by dx with some change in the position, it's changing. Okay, so the change of energy with respect to position is a force into displacement is a work done. So let me call it as a internal change in small microscopic work done. Okay, right? So now I have a way to connect the first derivative to the work done. That is the, let me for the comfortability, let's say I want to find average work done. So which is summation meta er. Let me put this here, the dou er by dou x into dx divided by summation over minus beta er. Okay, which is what? I can again play the same trick. What is the trick I play is, okay, which would be 1 by beta z dou z by dou x into dx. Okay, so that means beta into average small work done is equal to derivative of x log of z with a dx. Okay, so what I have, this is the term, right? So I can just replace the first term with the beta into average work done or internal work done. Okay, now just to talk about the second term. The second term, what I have here, this is the term I have, right? This is the term I have. Okay, so for time being, let's consider derivative of change in log z is equal to beta d omega, right? Okay, minus e average into d beta. That is what I conclude. This is average energy. Okay, right? So average energy with a minus sign, so I have to put a minus sign here. By the way, product, if you just take the variation, I can simply write E variation like that. Okay, so what I have is E dB is equal to D minus beta dE prime, sorry, E average. Substitute this here, beta minus of my this is minus, okay, EB plus beta dE. Okay, so these two terms together, beta d of omega plus, sorry, d omega, d omega plus dE, right? Okay, let me write down that. Okay, and to send to the left hand side, okay, what is left is derivative of ln z plus this one you send to the left, E into beta. On the right is, what is left is beta, okay, d plus dE. Okay, so if you carefully look at this, we have a formula, the connection between ds, the change in entropy, with the change added heat. If you see this carefully, this is what? 1 over by k beta t. Okay, if you carefully see this, what I have here is S is log of Z plus average energy into beta multiplied by k beta. So this is the entropy actual expression in terms of partition function. See, knowing a partition function, I calculate energy and also I calculate entropy. Okay, so likewise, there are so many ways I can derive different physical parameters of the system in terms of a given partition function. Okay, so usually the entropy is given as S is equal to K log of number of accessible states for the system with some energy. This is the formula usually given. Okay, right. So which takes into this form in terms of partition function. You can just even derive this derivation possible. Okay, fine. Okay, so we have now established the power of partition function. Okay, right? So let's take a system where kinetic energies are involved, potential energies are involved. Okay, so what kind of system is that? Let's say take a simple pendulum. It can oscillate. Okay, energy of the pendulum I can write down. If the mass is there, angular frequency with which it oscillating. Okay, so what I will get is kinetic energy is p square by 2m plus half kx square, where k is the spring constant. Don't confuse with the Boltzmann constant. Okay, and interestingly, what you have find is omega square is equal to k by m. Angular frequency is connected to spring constant. So if I do that, I'll have p square by 2m plus half into m omega square x square. This is the overall energy of the system. Okay, of a spring, a simple pendulum system. Now, electron is oscillating about the nucleus. It's simple pendulum. It's like a harmonic oscillator. Okay, so classically, if I want to specify any particle, okay, whose energies are there. So let's say I represent energy of a particle located at Q1 and P1 location. And there is one more particle also there added to the system, Q1, P2. And there is up to n particles I have. This is the overall energy. Okay, so let's do one thing, one interesting power of partition function we will see. Let's say I'm able to separate one entity or one atom out of the collection and put it separately. Okay, so let me call E is energy of ith atom and corresponding Pi Qi. Okay, right? So plus E prime, where E prime would be function of Q1 Qi minus 1 Qi plus 1. Similarly, P1 Pi minus 1 Pi plus 1 up to P up to so on. Okay, depending on number of the system. Okay, for timing, let me concentrate. System has only kinetic energy, no potential energy. Okay, so there is no dependence on Q. Okay, so where E of I can represent as B into some P square, because some constant 2 by m 1 by 2m is there. Let me capture that into beta. Okay, now what is the chance of that particle can have energy small ei? How do I find? I'll find average of it using the same Gibbs distribution, where dq to dqi minus 1 dqi plus 1 dp1 dpn. Okay, right? So here there is a pi plus pi minus 1 dp dpi plus 1. So the one which is right, okay, divided by, so sorry, it is not there. Everything is there. Okay, let me remove that. Okay, up to dqn dp1 to dpn. Okay, this is what I want to write. Now what I'll do, denominator also I have some summation. What I'll do, I can separate now as summation beta ei, substitute explicitly what is ei dpi divided by pi dpi summation, sorry, integration exponential minus beta e primes. Okay, what is e prime? E prime is these things. Okay, and denominator also will have exponential b primes with the corresponding dq's dp's. So these two things are common. I'll get rid of it. Okay, so what I'll have, this is just like earlier I had, I'll play the same trick of the partition function. It can be represented by minus 1 or dou by dou b log of, okay, log of the integrand, okay, exponential minus beta e of I dpi, okay, right? So log of exponential is there, na? So what I left with is exponential minus beta ei dpi, which is actually minus infinity to infinity minus beta into, okay, beta into bpi square into dpi. Okay, so let me use this into simpler form. Okay, use it to simpler form is like call it as call it as uh, minus integration, okay, e to the power of minus by square dy, where y is beta into beta, sorry, square root of beta into y is pi's, okay, so pi square, okay, so something like that. So basically, if I don't have beta here, this is actually 1 square root of pi. How? Very simple. If I, let me call it as some I square, I can introduce as square some squares of two integrands like this. I'll use the dummy variables, which is equal to double integral exponential minus x square plus y square dx dy. Okay, if you carefully see, sorry, x square plus y square is a radius square. So if I introduce x equal to r cos theta, y equal to r sin theta, and run r from 0 to infinity, theta from 0 to 2 pi. So above integrand would convert into partial, sorry, polar coordinate system as, okay, exponential minus r square, okay, and dx would be dx dy would be r dr d theta. How? I just take r, okay, if this is r, this would be dr, okay. If I change a small angle theta, the arc, this arc is r into d theta. So I want to calculate this volume surface element, which is this. So I want to cover the entire surface. That's why I just increase the r and theta like that. Okay. So if you integrate straight away, so integration of dt is d theta would give me 2 pi. Integration from 0 to infinity e minus r square r into dr. If you substitute r square is equal to t, 2 dr dr is equal to dt, r dr is dt by 2. So what I'll get? 1 over 2 integration, okay, 0 to infinity. The integrations remain, the limits remain same, e minus t into dt. 2 cancels, pi integration of exponential of t is just exponential of minus t divided by minus 1, 0 to infinity, okay, which is minus exponential of minus infinity exponential of 0, so which is minus, okay, which is equal to pi. I square is pi, okay, so I square is pi, I is square root of pi, okay. So square root of pi I got. If I have some factor inside, that factor would come in the denominator. Okay, how it will come is okay, how it will come is whatever is the factor is there, it will come as a square root of that factor. So there is a square root, beta b is there, that will come as a square root of b. So here, interestingly, what you can find is the energy of the average energy of the system would comes out to be half into k Belgium into k. This is a value. So what it says is, in the energy expression, if there are terms with the quadratic dependence on coordinates. Example is p square by 2m. I just saw pi square by 2m. That is the kinetic energy is quadratic dependence. In that case, okay, each term would contribute same amount of energy irrespective of their location, irrespective of their momentum. Okay, so all of them are equiprobable, all of them contribute equal amount of energy. Okay, so that is actually called equipartition theorem. Equipartition theorem comes from partition function, power of partition function, you can say. Okay, right, fine. So let's try to understand a little bit more using a classical limit. Okay, so let me use my hand notes. Instead of writing things, it is much quicker. Okay, right, so we covered up to here. Yeah, okay. Now for example, here you see, let's say atom is there, atom's ground state energy, excited state energy is separated, and higher order orbits are there. If the temperature is raised, what happens? Electron can go to higher orbits. If temperature is low, electron can exist in the lower orbit. Okay, so the thermal energy is k beta T. Okay, and energy separation is between the atomic states, ground, excited. So this is delta E. Okay, now the temperature has a lot of saying in it. If the temperature is so high, this quantity is much larger than the separation. So what happens? The electron would jump to higher orbits. Okay, so an electron would jump to higher orbits. Fine. So it will jump electron because the separation is much smaller as you go to higher and higher levels of an atom. Okay, right? So the mean kinetic energy, for example, in the case of a single atom, would consisting of px square plus py square plus pz square by 2m. Contribution comes from all the three coordinates x, y, and z. So each coordinate, momentum coordinate, contributes 1 over k beta T energy. So all the three together contributes 3 by k beta. So there's a mean kinetic energy is this quantity. Okay, so that is why as the temperature is increasing, the kinetic energy is increasing. System goes out of that. Okay, so classical limit, this is obtained when the temperatures are very high. High T implies classicality. Okay, a small t implies quantumness. Why? Because as the things goes like temperature increases, the electron goes high. There is no need, like no need of description of single orbit. It becomes a band of orbits. So there, the idea of quantumness is no more like no more what is the word relevance. Okay, if the temperature is low, quantumness is there, it becomes relevant. Okay, right? So for example, a single classical harmonic oscillator case, right? Harmonic oscillator case. Okay, so let me describe. For the harmonic oscillator case, energy is p square by 2m plus half m omega square x square. Okay, so this would contribute, as per the equipartition theorem, half k beta t. This would contribute half k beta t in the mean energies. So what is the total mean energy? Will be just a k beta t. Okay, so now that is a classical way of saying. Quantum mechanically what? Quantum mechanical is En n plus half into h omega, right? So this is a quantum mechanical energy. Now what is the average energy of it? So what I'll have, I'll bring the probability distribution, n tends to 0 to infinity, E minus En divided by n range minus beta En, which is again simply this is z. So what I can write it as minus dou beta log of z. Okay, right? So I just want to know now how to take a log of z. I want to know, right? And also I want to also know how to I also want to know how to differentiate that with respect to d beta. I want to know. Okay, so for that, what one can do is, let's take z, take out exponential minus beta h omega divided by 2 from there. Okay, where En is n plus half into h omega, right? Okay, so when I substitute this in the expression, I'll have 1 plus, okay, summation over e to the power of minus beta n h omega. Okay, the two terms are there. One term is independent of n, so that I taken out. So which is equal to, I'm done. Okay, it doesn't go anymore. Okay, I have to finish it here. E to the power of minus beta h omega by 2. Okay, summation, like say some x of n, where x's are, okay, e to the power of minus beta h cross omega. So which is simply z is equal to, right, z is equal to x minus beta h omega by 2 multiplied by 1 by e minus beta h omega. Okay, so this is 1 by 1 minus x, right? Okay, so from that I'll get this. Now let me try to find exponential, log of z. Okay, let me take out a new one. Okay, new one. Now I have a z which is exponential minus beta h omega divided by 1 minus e beta h omega. This is I have. Okay, now I want to find log of z. What I'll get is minus half beta h omega minus log 1 minus e beta h omega. Okay. Okay, this is some problem. Okay, let me use my notes quickly. That way it's easier. Okay. Right, so I have what is Z expression. So I want to take a log of Z. Okay. When I take a log of Z, okay, so I can just simplify into this form, right? And take a derivative with a beta, I'll have h omega multiplied by half plus 1 by e to the power of beta h omega minus 1. This is left. Okay. Now, very important thing here is, for a given temperature, what is the situation? If the T is very, very high, then beta h omega is very, very small. In that case, I can simplify the things to get the average energy or a mean energy as into kT. This is the classical limit. Okay. If the other way around, let's say temperature is so small, in that case, exponential beta h omega would be very large. So exponential beta h omega minus 1 is just exponential beta h omega. And overall energy, a mean energy, would comes down to be this expression. Okay. Right? When you go to temperature so small, T tends to 0, beta tends to infinity, exponential minus beta h omega is 0. So I'll get back the 0 point energy come from here. Okay, where is that energy expression for the here? Okay, so this is the energy expression I had. I'll get back when n equal to 0, that is the 0 point energy, right? So n equal to 0 correspond to E0 h omega. It's called 0 point energy. Even temperature is 0, system would exist with zero energy, sorry, some energy, h omega energy. So that is because the things are very much quantum in nature. Okay, fine. So let's get back to the notes. Right. So I think I'll stop at this point here. If I'll just see if there are some questions. How is energy changing when N, V, and T are constant? What is the source of change? Ah, very good. Very good. That is a good question. Okay. So, yeah. Okay, let me get back. And let me use my notes somewhere. I think it is in yesterday's class, no? Yeah. You see here. Take this simple example. How many number of particles I have? Say 3. Okay. Let's say they're confined to certain volume and the temperature is constant. Okay. So let's forget about the total energy column. Just forget about the total energy column. Okay. Right. The right side column you just forget about. Now, okay. Now, out of 3, if I allow them to rearrange as per their wish, okay, they can arrange all aligned and total magnetic moment is 3 mu. Okay, they can arrange. Okay, just a minute. Yeah, they can arrange one of them misaligned to the other 2 and can have energy like this. Okay, can have energy like this. How did I put a color? Highlighter. Okay, no, not possible. But anyway, forget about it. If two of them are misaligned or two of them are in the negative, another one is positive, I have the fifth option. And I have sixth option. I have seventh option. So you see what is the magnetic moment associated is some mu. Okay, the arrangement gives a different magnetic moment. The magnetic moment itself is connected to the internal energy. So I have a different internal energy even when system is not interacting with the environment. No reservoir, no extramagnetic field is there. Even in that case, the available magnetic moment is actually represented in the third column. That means the total energy of the system is also varies like that. But remember, it is fixed between some value to some value. Here you say total magnetic moment is fixed between -3 mu to 3 mu. At a given state, let's say all are aligned in same fashion, right? In that case, the total magnetic momentum is fixed, either 3 mu or a -3 mu. Okay, right? It is fixed. It is not going to vary because there is no one is actually coming in and supporting the system to take a different state, and different state has to be taken at the cost of acquiring some energy from the outside. But randomly they can arrange. They can arrange in various fashions. So the accessible states are there. Here there are 8 accessible states for 3 qubits, for example, 3 electrons. Okay, so that is how fixed n, fixed v, fixed t could even allow the source to change, the system to change into different energy values. Okay, right? Okay, then did you mean it peaks with a large beta? Okay. I mean, I think you are talking about yeah, I think you're talking about peak. I think yeah, here, not here. Let me use my hand note. Look at here. I talked the peaking when it comes to, yeah, here I think I talked about here. Okay, if you just see the probability of particular energy E is actually a product of two functions. One is omega of E, that is the number of accessible states multiplied by exponential minus beta E, where omega of E is increasing function, beta E, exponential minus beta E, is decreasing function. The product would be like one is increasing, another one is decreasing. I think I had drawn that nicely somewhere. Why? Okay. Yeah, it is before this. Yes, you see? Yeah. One is increasing, another one is decreasing. When you talk about the product, it will be increasing and decreasing. It peaks. Okay. Where it peaks at the average energy. E equal to E average. Okay. So it peaks at that energy. If the average energy is very high, that means peak is the system is very linear. Okay, so average energy is high means the magnetic energy is high, thermal energy is low. Okay, thermal energy is low means, sorry, thermal energy low means, okay, so K of T is actually the thermal energy. So if the T is low, thermal energy is low. If T is high, thermal energy is high. So what you are saying is, with respect to beta, probably you can connect the peaks, whether it is peaking. Okay. Yeah, you are right. And is energy E on the x-axis? Okay, so in which case, no, energy is on the, sorry, x-axis, yes, absolutely right. And on the y-axis, I have a probability, P of R. Okay, right. And please go through by the notes which I am going to share today. Okay, So it is neatly explained everything what I am wrote in my hand notes today. So this lecture notes would explain everything. Okay. As a distribution of energy changes based on temperature, okay, the energy distribution becomes function of temperature. Okay, so we can find out the transition temperature on which system changes from classical to quantum. Okay, remember the classical to quantum conversion would happen. Okay, right, right. So even if you just take a classical scenario, sorry, quantum scenario, where the levels are like this, atomic levels. Okay, right, these are unequally spaced, you see, right. At very low temperature, things are very much probabilistic, and sorry, at very small level, atomic level, probabilistic, and the temperature is also, I'll choose very cool, just like a quantum hardware. So there I'll have, this is a delta E. Okay, so if the temperature is low, how much amount of energy is supplied with the temperature around is represented by K beta T. Okay, Boltzmann constant into temperature. If this is so smaller than delta E, electron would not jump. No jump. No jump of electrons. Let's say if T is increasing, so what happens? Average energy of a collection of atoms would fall somewhere here. Let's say average energy is here. Okay, so what is the average, like what is the spacing around that point? This is the spacing. Let me call E1. Okay, so the temperature here, right, this delta is large, but this delta is smaller, so K beta T is larger than delta E1. So what happens? Electron would easily jump to higher orbits with the increase in temperature. So as you go higher and higher with a large temperature, what happens? I don't have any more discreteness. I'll have a continuous band. Okay, continuous band means electron can exist anywhere here. There is no particular orbit. So the quantumness is gone. Okay, right? So that is what happens when you increase the temperature. Even when you are talking quantum mechanically with low T, if the temperature rises, then there is no point in just dwindling with the quantum mechanics anymore. Then classicality would come, classical physics should be used, appears, classicality would appears. So there is no point in talking about discreteness, talking about the eigenfunctions and all those things is no more valid. So only thing valid there is classical physics. You should talk about a bunch of atoms existing in the electrons existing in particular band. Okay, right, fine. So that is like classical mechanics, classical mechanical description leads to or transforms to quantum to classical transformation happens, quantum classical description, when T is increased. Okay, T increased. If T is low, I can still exist in the classical quantum description. So that is why all the quantum hardware, like say qubit, which are realized in, let's say in the case of transmons in the IBM, let's say you talk about 5 qubit system, Q2, Q3, Q4, Q5. Okay, right? So, okay, right? So, okay, this is, so in that case, okay, the temperature has to be so small and I want to confine at a quantum level things to behave quantum mechanically, not classically. So that's why temperature plays a very, very vital role. Okay, fine. So yeah, yes. And is there any other question? Is rearrange is due to external influence or energy? Yeah, rearrange probably may not be due to external influence. Usually rearrangement would happen with external influence for sure. Okay, if I don't involve the external involvement, let's say system is isolated, even in that case also things can rearrange by itself. That is probably because of small internal weak interactions. Okay, that is what led to this case, na, like I said yesterday, this case, right? Forget about the last column. Last column is due to the external field. Okay, external field is there. In that case, there is like I can ensure only particular scenarios. Na? If I don't, I'll have all the 8 scenarios. Okay, so if I leave the system, it can rearrange itself randomly. That is what leads to paramagnetism. Okay. Okay, can we find the critical temperature when at quantumness is lost? Yeah, beautiful question. Yeah, absolutely. Okay, so yes, you can find definitely. So how it is done is, I think I will discuss this in tomorrow's session. I think. Okay, how transformation of classicality to quantum to classicality would happen. So that is where temperatures become so high. Okay, so for a particular scenario only we can talk about, for example, a particular atom, what is the critical temperature, where I, like say if I just take hydrogen atoms, at what temperature I can't talk about any quantumness of it. Okay, so that is all connected with its internal delta E. Okay, if the delta E of the hydrogen atoms is much larger than the thermal energy given at certain temperature, still in that case I can have a quantumness intact. If I don't, then I can't use quantumness anymore. The classical picture has to be used. Okay, right? So yeah, the answer to your question is I think AK Jha, critical temperature could be easily found for a specific scenario. So it is, critical temperature is not a generic term. It is associated with a different kind of materials. That is what electromagnetism, critical temperatures are there. So for a particular material, there is a particular critical temperature. Yeah. Okay. Okay, so I'm sorry about too much of mathematics. Okay, the statistical physics, it's itself a lot of mathematics. I tried my very best to simplify things and derive, and my lecture notes would have more details. Okay, so you will understand more of it when you go through line by line. Okay, right? So what we'll do in tomorrow's session is we'll use the Gibbs principle, that is canonical distribution, and apply the Gibbs principle to the classical system, that is harmonic oscillator, classical harmonic oscillator. Whatever we did today, in a different way, we will do the same. Okay, and then we'll apply the same to quantum harmonic oscillator. Okay, classical harmonic oscillator and then quantum harmonic oscillator. We'll do both tomorrow. So that is a part of the commitment we are planning. So we'll see how the canonical distribution would give different scenarios, different values in these scenarios. Okay, so then we will go further and we'll study the power of partition function, and we'll study its properties. Okay, in various scenarios, how it can lead to some interesting cases. Okay, whatever done today, again let's do it today in a different aspect so that you will develop a better understanding. Okay, and there is something called a Gibbs paradox. Means Gibbs paradox in the sense the system entropy is supposed to become a constant as temperature is reduced to zero values. Okay, right? So that is the law of thermodynamics. Okay, and if this, let's say, if I just take two systems together of equal number of atoms, equal volume, and then just club together, and the total entropy should usually sum. Okay, but when you use identical particle, if you use indestructibility of the particles, then you might end up with the wrong conclusion that entropy is actually entropy is actually increase by some quantity, but that is not the case, and we'll just discuss that in tomorrow's class. Okay, right? So what I'll do, I'll upload the tomorrow's lecture notes today itself. Okay, right? And like I said, I am using the book by Reef. That is also I just given as a reference. You available on the net. You can just check that. And tomorrow's class, what you can do, you can go through the today's, like whatever I'm uploading in advance. In tomorrow's class, we can quickly derive what I meant. Okay, fine. I'll stop here. It's already 5 minutes past 4, and I have tried my best to answer all the questions. Okay, right? And we'll meet tomorrow.
Thank you so much, sir. It was a wonderful session, and thank you for even providing slides of tomorrow's class today only. So we'll upload it, and then participants will be benefited from it for sure.
Yeah, thank you. Thank you.
Thank you, Ashish sir, also for joining. So we'll continue tomorrow. And in case if your quiz is still pending, I request all of you to give it before tonight. Thank you.